So welcome everybody to this seminar. I'm very happy that we are all here and that we have William Sari as our seminar speaker today. So I will just briefly introduce him. William Sari received his doctorate degree in astrophysics in 1998 from the Hebrew University of Jerusalem. He completed his postdoc at the Caltech, or the California Institute of Technology, where he was then appointed in 2003 as an associate professor in astrophysics and planetary studies. In 2007, he was then appointed a full professor in astrophysics at the Hebrew University of Jerusalem, where he is today. Ray-M, he works on a variety of areas, for example, massive stars and their explosions, then the birth of black holes, the dynamics of galaxies and stars, planets, and also exoplanets. So Ray-M Sari won numerous awards, including the American Astronomical Society Warner Prize Association in 2006, the Frankel Prize of American Association of Physics in 2007, the Outstanding Investigator Award, the Guggenheim Award, Radcliffe, and Michael Bruno Award. So a long list of very prestigious awards. And he also holds research grants, including national and ERC grants. So Ray-M Sari, we are very happy to have you here, and the screen is yours.
Thank you very much. I'm happy to give this talk, though I would have been more happy to give this talk in person and visit you, but I was promised this will still happen. So yeah. Everything is okay. And today I'm going to talk about things that are happening in the center of galaxies, and particularly the center of our galaxy. For those that are not working in this area, even maybe the title with all this acronym needs some explanation. So these are all things that are happening around the black hole in the galaxy center. TDE, tidal disruption events, stars coming very close to the black hole and basically explode or getting torn apart by the tides of the black hole. MRIs, which are extreme mass ratio inspiral, which is an object going around the black hole, the supermassive black hole in the galactic center, emitting gravitational waves, and its orbit shrinks, eventually merging with the black hole. We will be particularly interested in a special kind of MRIs, which are stellar MRIs. Usually people talk about compact object doing that in spiral, but we will also think what happens if a star does that in spiral, and what is the rate at which such a thing may happen. Plunges, which are direct collision, if you want, between a star or a compact object and the supermassive black hole. So instead of coming in circles, going through a more radial orbit and hitting the black hole, and maybe mass transfer between a star and the supermassive black hole. So all of this is happening, or sometimes happening, in the galactic center. Actually, there are even more things like hypervelocity stars, which are stars ejected at velocities of 1,000 or more kilometers per second out of the galaxy due to things that are happening in the galactic center. So I'll try to see how all these things are related to each other and what are the dynamics that are involved in producing those events. Okay, let me skip that one. So here's a movie made by the Garching Group of a journey to the galactic center, more or less from the point of view where we are. And these are farther and farther zooming to the galactic center, showing you the difficulty of actually making observations there. The galactic center has a lot of dust in it, so it's opaque. So at some stage, this movie switches to the infrared, which is more transparent. The dust is more transparent to the infrared, and you can see the inner parsec, even fractions of the inner parsecs. And eventually you go so close to the supermassive black hole that the orbital time becomes so short that you can actually see the motion of stars on the lifetime of the researchers or the graduate student or whatever. And you can fit these orbits with more or less Keplerian ellipses. And in more accurate cases, you even have to use GR. And that gives you information about the black hole in the center of our galaxy. There is another observational group competing, basically, doing similar kinds of observations, the UCLA group with Andrea Ghez. And overall, we have 20 or a little bit more, 25 years of observations of the galactic center, where some of the stars have already completed more than a full orbit around the supermassive black hole. And I'm sure everybody's familiar. This was the topic of the Nobel Prize given to at least the right two people here, Reinhard Genzel and Andrea Ghez. And if I have to summarize in one slide, what is this Nobel Prize given for? It's basically the central image here, the central figure, which is the measurement of the star, one specific star with short enough orbital period called SO2. And the star, you can see the star orbiting as an ellipse on the sky, and the black hole is marked there at 0, 0. You may wonder why the black hole is not on the main axis of the ellipse, and it's not in the focus of that ellipse, in any of the foci of that ellipse. And this is just a projection effect. If you take an ellipse on the sky and you project it, then the foci doesn't become the foci of the projected ellipse. But this is an okay Keplerian orbit. And basically by measuring the orbital period and the size of the orbit from Newton's law or Kepler's law, you can get the mass of the black hole. It's a little bit more involved. You actually need to measure radial velocities because you can't know the actual size of the orbit. You just see the size of the orbit on the sky. You don't have a physical size. If you had a physical size, that would have been enough. But since we don't know the distance to the galactic center, just by seeing the motion of the star on the sky, we have the angular size of the orbit, but not the physical size. But you can measure radial velocity, and this is how you get a scale. So a combination of the velocities, and which is the image on the right here, and the shape and size of the orbit on the sky, you can get the mass of the supermassive black hole, which is around 4 million times the mass of our sun. The Schwarzschild radius of such a black hole is 0.1 AU. And the orbit of that nearby star is very close to that of the black hole, but not too close. So the periapse distance is 100 AU, still much farther than the Schwarzschild radius. So this is not as close as you can get. In principle, you can be much closer. The tidal radius, how far that star has to go in order to be torn apart by tides from the black hole, is about 1 AU. So about 10 times the Schwarzschild radius, and that number will come out later. But the periapse distance, this 100 AU, is still 100 times larger than the tidal radius. So the star is safe. It's not going to be torn by the black hole. It's moving more or less on a Keplerian orbit. In fact, when I prepared this slide several years ago, I wrote what is the future holding, but some of this thing already became past. So you can see the gravitational redshift of the light coming from the SO2 star to us, and that is already measured. It's the gravitational redshift of the supermassive black hole, mostly when the SO2 star is at periapse. And you can already measure the precession of the SO2 star on the sky, the Schwarzschild precession. This was expected and it's now measured, so it confirms general theory of relativity. No surprises there. I think the next thing we're really hoping for, but it will require, it's much more involved, would be to see the precession, not just due to the mass of the black hole, but due to the spin of the black hole. And basically, this will allow us to measure the black hole spin, but that's a much harder measurement, and it's probably not, they won't be able to do that with the SO2 star because the effect is too weak. The hope is that maybe they will be able to find a star even closer to the supermassive black hole, for which the GR effects are stronger, and therefore we'll be able to measure the spin of the black hole, maybe allowing us to know how that black hole formed, and so on. Okay. So what are the phenomena that are happening in the galactic center? Most of them are destructive phenomena. Let me go through some of them. So if there is a star, like the one depicted in this figure, orbiting the supermassive black hole, if it's close enough, basically if it's at its tidal radius, or in another language, if it's filling its Roche lobe, mass will start to flow towards the black hole from the star through the point, a Lagrange point called the L1 point. I think we're all familiar with that, probably leading to a formation of an accretion disk around the supermassive black hole. Maybe some jets will come out of that. And what I'm showing here in this figure is an outer ring, because I'll show you at the circumstances of such an extreme mass ratio between the donor and the receiver, there might be leakage of mass outward rather than inward through the L2 point. I'll try to discuss that. So this will be one issue about mass transfer. And also, if there is a star like that that is so close to the supermassive black hole, there will be emission of gravitational waves at a level that we can detect, even from a tiny object like a single star. If it's around the supermassive black hole in our galaxy or even in Andromeda, it is in principle detected not by LIGO but by LISA, because the supermassive black hole is so large, the frequency, the orbital time of orbiting around it is much longer, the frequency is much smaller, suitable for LISA. Tidal disruption events is something that we haven't seen in our galaxy. This is something that happens once in 10 to the 5 years in a galaxy. So we'll wait long enough, we'll see it, but we can see it in other galaxies. I'll try to explain where is that number of 10 to the 5 years coming from and what it depends on. And a similar process, which is the breakup of a binary rather than a single star, is the same story, because it's gravity. Instead of holding a single object, it's holding a binary to orbit around each other. And when that binary comes close enough to the supermassive black hole, the tides tear apart the binary rather than tearing apart each individual star. Of course, because the binary is wider than the size of each object, it doesn't have to get so close to the supermassive black hole. So the effective tidal radius for the binary is larger than the tidal radius for destruction of each star individually. And when such a binary is broken apart, two interesting phenomena are happening, which will be relevant to the things I would like to discuss. One is that one of the stars becomes unbound. It becomes a hypervelocity star. So that's a topic of research which is interesting for itself. These are stars flying at thousands of kilometers per second away from the galaxy. And we see such stars flying away from our galaxy, and we think this is a possible mechanism to form them. And the other thing, it's a way to put the other companion, the one that was not ejected as a hypervelocity star, as a tightly bound star to the supermassive black hole, which may be that in other ways was difficult to form. And then I'll also try to talk about the rate of plunges of stars coming directly into the black hole, either compact object or stars. And through this talk, this diagram here on the right will escort us through this journey. And this is a diagram that basically, between the X and the Y axis, it gives you a description of all the possible orbits around the supermassive black hole. So if you think of an orbit around the supermassive black hole as an ellipse, you would like to characterize that ellipse in two ways. One, the semi-major axis, which dictates the period of the orbit. This is the x-axis. And the y-axis is the periapse, how elongated the ellipse is. So if the periapse and the semi-major axis are the same, this will be this line. These are circular orbits. Periapse larger than semi-major axis is impossible, so this is empty. Anything below here, far from the circular line, are extremely elongated ellipses. So this point, for example, is something that has semi-major axis of 10 to the 6 Schwarzschild radius, but periapse of just 10 Schwarzschild radius. You remember 10 Schwarzschild radii is about the tidal radius. So this is where stars are being destroyed. So main sequence stars cannot exist in this region. Compact objects can. They will not be destroyed by tides anywhere around that supermassive black hole. So I'll try to describe what is happening in this diagram, how things flow there, and how do you produce tidal disruption events, how you produce these MRIs, so stars moving on circular orbits spiraling slowly in towards the supermassive black hole. What are the sources of all these objects? All these processes are destructive processes. So even if you started with a system that had objects on these deadly orbits, they are long gone, and you need to repopulate them again with new objects. So the dynamic that does that repopulation is going to be a major part of this talk. The orbital periods, so let's see at what distances are we interested from the supermassive black hole. This talk I will be interested in the inner parsec. In why 1 parsec? This is the radius of influence of the supermassive black hole. In other words, this is the distance from the supermassive black hole at which the mass of stars is roughly equal to the mass of the black hole. So anywhere internal to that 1 parsec, most of the mass is the mass of the supermassive black hole. And you can think of the objects as more or less moving on Keplerian orbits. Farther away, the mass is given by the stars rather than by the supermassive black hole, and that will be not discussed in this talk. So if you look at this figure again, you'll see that I limited the x-axis and the y-axis at 4 times 10 to the 6, which is that 1 parsec compared to the Schwarzschild radius. So coincidentally, for our galactic center, there are 2 numbers which are both 4 times 10 to the 6. This is the mass of the supermassive black hole, so the mass ratio between the supermassive black hole and the typical star, and also the ratio between the size of the radius of influence and the Schwarzschild radius. Both happen to be 4 times 10 to the 6, as much as I can see just by a coincidence. Okay, so we know about gravitational waves, we know about all the activity that LIGO is doing at gravitational waves, but I'll skip that and I'll talk on the left side here about the possibility of detecting lower frequency gravitational waves by a much larger detector, maybe 3 detectors flying around the sun, trailing the Earth orbit, or some other configuration that I will come up with, and measuring the arm length of this equilateral triangle, and seeing those changes indicates that a gravitational wave is going through the system, and the frequency, the size of this triangle is set such that it will be able to measure frequencies compatible with the orbital time around supermassive black hole. The main thing they're going to look at is maybe coalescence of supermassive black holes. But if it's close enough, like in the center of our galaxy, you can see a supermassive black hole with even a tiny object, like a star, orbiting it. LISA would be sensitive enough to detect it. This is a diagram basically showing this. Even in Andromeda or in the Milky Way, the strain that you will get from the gravitational wave emitted by the object in these 2 distances exceeds significantly what LISA, the sensitivity of LISA. So when it's far away, not, but as the object spirals in, the frequency of the orbit increases. So the frequency goes from 10 to the minus 6 to 10 to the minus 4. Here it merges with the supermassive black hole. But throughout this region, you can detect that motion. So the question is, do we have a star so close to the supermassive black hole that currently emit gravitational waves that LISA can measure? Well, we had an image before of all the stars in the galactic center, but we're only able to see through the amount of dust that is there, massive enough stars, 3, 5 solar masses. Half a solar mass object you will not be able to see at the center of the galaxy, and it might be there. So I'll try to theoretically argue whether such a star is there or not. I'll show that the probability is small but not tiny. So there is order unity or slightly less chance that there is a star there orbiting the supermassive black hole so closely that it emits gravitational waves in the LISA detectable frequencies, and the intensity is also relevant. So if that will happen, this will be very cool. So let's discuss this possibility that there is a star orbiting the supermassive black hole and shedding mass onto that supermassive black hole. So this is actually an image that I took from the internet of an X-ray binary, not the supermassive black hole, but it's the same physics, except that this is now much bigger than this. So just the scale is different. And we're all familiar with that. There is a mass transfer through the L1 point. So if you walk on the rotating frame, so think of the supermassive black hole or the black hole and the star as orbiting on a circular orbit. Put yourself in that rotating frame, so you have the two objects stationary. There is a point where the balance, the gravity from the two objects and the centrifugal forces balances. This is the L1 point. It's a stationary point in that rotating system. And if the star is big enough, mass comes out through the L1 point and spills to the more massive object, creating probably an accretion disk around it and eventually accreted into it. This is the familiar picture. What I would like to argue is that, I'll stay on this for another second, that in the case of a massive star orbiting the supermassive black hole, there will be leakage not only of mass through this point, but also through the L2 point, which is somewhat higher potential, so it's usually a little bit harder. But the mass transfer in the supermassive black hole case is fast enough that you're trying to spill the mass so quickly that you overfill this narrow point, and you also spill mass through the other side. So we'll talk about that. Okay, so this transfer of mass is a stable mass transfer. The orbit evolves due to gravitational waves. In other cases, in planetary cases, it can evolve through tides, but here we're talking about an object that loses angular momentum by emitting gravitational wave, and that tends to shrink the orbit. On the other hand, as it transfers mass through the L1 point, it can gain specific angular momentum, so it can lose mass with more angular momentum and gain angular momentum and evolve the orbit outward. And there is a balance between those two effects. And to keep the stable mass transfer, the object has to move in or out so that it always fills the Roche lobe. Because if it wouldn't fill the Roche lobe, it would emit gravitational waves, the orbit will shrink, and the Roche lobe will shrink with the orbit, and the star will fill the Roche lobe, so this is a stable process. So how does the size of a star change as you take mass away from it? And you can think of two ways. If you think of main sequence stars, we know that there is a mass-radius relation, roughly like this. So the radius is almost linear with the mass, more accurately like 0.8. And the reason is that these main sequence stars are hydrogen burning, so they have a constant temperature at their center, which is the temperature for efficient hydrogen burning. So if you write the hydrostatic equilibrium and assume that the temperature is constant, you get that the radius and mass are proportional to each other if you say that the temperature is fixed. So this is for main sequence stars. The other thing that you may think is adiabatic expansion of a star. So if you take again the hydrostatic equilibrium equation, and you say that the pressure is changing like the density to the 5/3, adiabatic change of the pressure, you can get the relation between the mass and the radius. So comparing this to that, and you get that the radius goes like the mass to the -1/3. So if you do adiabatic changes, as you take mass out of the star is actually growing rather than shrinking. So which one of them is right? Adiabatic changes or moving along the main sequence? So it's a matter of time scale. If you do it slowly enough, you take mass away from a star slowly enough, on a time scale which is longer than the thermal time scale of the star readjusts itself and stays on the main sequence as a new lower mass star. So it moves along the main sequence, shrinking when the mass is going down. If you take the mass quickly enough, it reacts adiabatically. There is no time for the heat to transfer through the star itself, and therefore the star is actually growing as its mass is going down. So on any time scale between 3 hours and 1,000,000 years, which is the thermal time scale of the star, you'll have an adiabatic change. So when you look on different kinds of stars, shedding mass on the supermassive black hole, you can see that more massive stars have a short thermal time, and therefore they will emit gravitational wave, and the star will shrink as a new star on the main sequence. So you start with a star here. So let's see, what is this diagram? The x-axis is the mass of the star orbiting the supermassive black hole. And the y-axis is basically how it feels its Roche lobe and how far it is from the supermassive black hole. So as the star is shedding mass into the supermassive black hole, it gets closer and closer to the supermassive black hole. But then the emission of gravitational wave becomes so fast that it becomes on a time scale which is shorter than the Kelvin-Helmholtz time of the star, and the star starts to expand rather than to shrink. The result of that is that the orbital period of the star around the supermassive black hole will grow rather than decrease. So this will be a very unique signal of gravitational wave. Instead of a frequency going up, the frequency will go down. So if I take the usual chirp and I reverse it, I get a preach. So the stars will initially do the usual chirp, but towards the end, when they become small enough and the emission of gravitational waves becomes fast enough, they make a preach, evolving away from the supermassive black hole. So if there is a star like that on the center of our galaxy, it's going to be a fascinating event for LISA. And the inner workings, the thermal time of the star, affect the way its gravitational waves evolve. So I think that's pretty cool. So that's something on such a microscopic scale affects the macroscopic picture of how that star evolves around the supermassive black hole. And regarding the L1 and L2 point leakage, I found a 3D print of the Roche potential. So you can think of the supermassive black hole in here with a very deep minimum of the potential around there. You can think of the star as being here, and the material of the star is depicted here with this orange matter. And you see that there are two barriers for material to spill away from the star. There's a barrier at the L1 point, and there's a barrier at the L2 point. And as you can see from this diagram, the L1 barrier is slightly lower than the L2 barrier. And this is why mostly we have spillage of mass this way, and not the other way. But because gravitational waves are so effective and they shrink the Roche lobe around the star so quickly, then the amount by which the material will bypass this point will be so large that it will also bypass this other boundary. And therefore, you'll have leakage of mass also away from the supermassive black hole, creating an external disk, not only internal to the donor star. How am I doing with time here? Okay, wow, I have to, maybe I'll skip the hypervelocity stars. And the tidal disruption events, I already discussed them in generally at my opening. And let's go to the dynamics of how stars move in the galactic center. What are the main processes that govern that? And therefore, from that, we'll try to see how many spiralines like that we are expecting to find compared to star coming on very radial orbits and arriving the supermassive black hole to be torn like tidal disruption events. So a very important process that happens in the galactic center is a very simple two-body relaxation. So you have so many stars around the supermassive black hole. Actually, by definition, I have 4 × 10⁶ stars around the supermassive black hole. Why? Because I'm looking at the inner parsec, at the radius of influence of black hole, which by definition has the same mass as the mass of the black hole. So since the mass of the black hole is 4 × 10⁶ solar masses and the stars are just 1 solar mass, then I have 4 × 10⁶ object in my radius of influence. They go in random orbits around the supermassive black hole. They can scatter each other due to their own gravity. So it has a cross-section like this. If they have a velocity dispersion v, given by the distance from the black hole. This is the distance by which they can deflect each other significantly. Square that, that is the cross-section. Density times cross-section times velocity is the rate of scattering. So the time for strong scattering is this. And you can see that it is given roughly by this formula. So what is it here? P of r is the orbital period at that distance, whichever distance you're talking about. M over m is the mass ratio between the supermassive black hole and the star. So this is 4 × 10⁶. And this is the number of stars at that distance. And I think it is particularly interesting to think about this equation at the radius of influence, because several things cancel, and it's also the place that most of the activity is happening. So let's see, at the radius of influence, the orbital period is 10⁵ years. This is just set by the parameters of the problem, the mass of the black hole and the size of the radius of influence. So this is just a number, 10⁵ years. M over n is 4 × 10⁶. And the number of stars is also 4 × 10⁶. The fact that this and this are the same is the definition of the radius of influence. That's not a coincidence. So I go to the radius of influence where the number of stars has a total mass which is identical to the mass of the black hole. So this cancels one of the powers in here. And I get that the relaxation time is the orbital period at the radius of influence times the number of stars there, times another 4 million. This is the time to scatter all the stars. But if I just ask what is the time scale to scatter a single star, then it is shorter by the number of stars that are there. And therefore, it is just the orbital period at the radius of influence. So I get that in order to relax the whole inner parsec, I need a huge time, 10⁵ years times another 10⁶ years. So it's not even completely clear if the inner parsec is completely relaxed. But in order to have a one strong scattering, this is just the orbital time around the radius of influence, which is 10⁵ years. And you will see later that this is the reason why we have one scattering, one hypervelocity star per 10⁵ years, one tidal disruption event per 10⁵ years. This is basically just the orbital time at the radius of influence. Okay, what about the density of stars around the supermassive black hole? So if you look about the density of stars in the nuclear center, you will see a statement that it's 1,000,000 times bigger than the density locally. And this is more or less true because here we have one star every parsec, and there in the same parsec, we have something like several million stars. So it's 1,000,000 times denser than here. But actually, it's more extreme than that because there is a steep density profile from the radius of influence all the way to the Schwarzschild radius. Either like this one or like this one. I'll try to discuss shortly how those came to be. So that means that close to the Schwarzschild radius, the density is much higher, and it's actually billions of times the local density. Let me stay with this figure, with those equations for a little longer. So if you will take the number of stars at each radius and divide it by the relaxation time of that radius, so this is the rate at which you scatter all the stars. This is sort of what you can expect would be the flux of the stars. If you ask that to be a constant, that gives you the number of stars as the function of radius, or a density, and that gives you a density that goes like r to the minus more than 2. This was the initial guess of Peebles to estimate the density structure in the galactic center. But just a year after, Bacall and Wolf came and said, no, this solution is actually wrong. And because as the stars flow in, they become more and more energetic, like 1 over the distance. There is an energy barrier at the center, close to the black hole, and you have to diffuse all that energy out. And instead, if you take E of R times the number of stars divided by the relaxation time, ask that to be constant, you'll get this kind of power law. What we have found out in the work that we have recently done, both analytically and numerically, is that in a way, both results are right. It depends what is the source of particles and where are they flowing. So if you just have a supermassive black hole and you put a source of particles, of stars, at some distance from it, as they flow in and the orbits become more and more energetic, they hit the energy barrier, and therefore this power law is correct. But if from the injection point they need to diffuse out, there is no energy barrier because the energy is becoming smaller and smaller. And in fact, this power law is right. So I believe that at the galactic center, if the source of stars is not coming from the thermal bath of stars away from the radius of influence, but due to some injection of stars halfway through, and I'll describe what is that soon, then external to that region, you will have a steep power law of stars, and internal, you will have the standard Bacall-Wolf profile. As you saw in the diagram that I presented in the very beginning, we will be interested in very eccentric orbits that come very close to the black hole. For each of those eccentric orbits, you can ask what is the timescale by which gravitational waves change the orbit. And what a gravitational wave does to an eccentric orbit is mostly shrink the apoapse and circularize the orbit to a small circular orbit with a distance similar to the original periapse of the orbit. You can estimate the timescale for that. There is the two-body relaxation, which we just discussed, the time by which other stars change the orbit. And you can ask yourself where those two timescales equal and get a simple equation like that. It's a surprising equation, but I'll show you the result for that in the figure. So this is the figure that we discussed already at the very beginning. So let's see what are the things in here. This is the semi-major axis, the distance from the supermassive black hole, and this is the periapse. These are when those two are equal, so these are circular orbits, and everything much below that line are very, very eccentric orbits. So for eccentric orbits, scattering between two stars, they change the energy and they change the angular momentum, but because of the huge eccentricity of the orbit, the angular momentum is tiny. So tiny changes in the angular momentum are important while the energy is not so tiny. So two-body scattering for extremely eccentric orbit change the angular momentum but do not change the energy. So basically what two-body scattering is doing is moving a particle up and down in that diagram, not so much left or right. Okay, so it changes just the periapse, not the apoapse. Gravitational waves, on the other hand, they take an eccentric orbit and they shrink just the apoapse, circularizing it to a circular orbit with the original periapse. So it's very nice to present it in this diagram because it means two-body scattering causes the object to go up and down, and gravitational waves pull the orbit to the left, circularizing the orbit. So moving to the left is shrinking the semi-major axis at a constant periapse. And the result that I've shown before, this one here, is this blue line here, separating the region where two-body scattering is important, therefore stars go up and down randomly by scattering, and the region where gravitational waves are important, where stars are being pulled to the left, circularizing their orbits just by the emission of gravitational waves. And this line separates the two. So let's take a few stars as example. Let's take a star in here that started on a circular orbit around the radius of influence. What's affecting that star? Gravitational waves are negligible because we're way above the blue line, only two-body scattering. So it goes up and down along this line, and it will eventually hit the tidal limit and will die as a tidal disruption event. And the time scale at which it will happen is basically the orbital time at the radius of influence of the black hole, as we showed before. So once every 10 to the 5 years, you will get a star coming all the way from here and getting torn apart here. If the orbit is much closer to the black hole, I will argue soon 100 times closer, then the star will be scattered by other stars, so up and down randomly. But before it manages to hit the tidal radius, it will hit this blue line, which means gravitational waves become more important than two-body scattering, and will just turn to the left and become a circular orbit, very tight to the supermassive black hole, and then continue to emit gravitational wave from a circular orbit, becoming that MRI that we discussed before. So now we can work from this diagram, what is the ratio between how many MRIs we have and how many stars that will come and be destroyed like a tidal disruption events. Most of the stars are in the outskirts of the supermassive black hole, so they are here. And this is the main thing that is going to happen once every 10 to the 5 years. And those are the sources, that's the main source of stars that will randomly move up and down by two-body scattering, but then eventually will arrive to the place that the periapse is so small that gravitational wave circularizes the orbits and they become MRIs. So these are the sources of tidal disruption events, and these are the sources of MRIs. And by knowing the slope of that line, we can figure out the ratio between the rates of those two events. And that comes to be just the ratio between the Schwarzschild radius and the tidal radius squared. So for main sequence stars, where the tidal radius is about 10 times the Schwarzschild radius, that means that only 1% of the stars will end their life as MRIs compared to most of them which will end their lives as tidal disruption events. Okay, if we go back to binaries, let me skip resonant relaxation. If we add the fact that some of the stars in the galactic center are binaries, starting at the radius of influence. So now think of an object going up and down on this diagram by scattering around other stars by two-body relaxation. But now this object is not a single star, it's a binary. So before it hits the tidal radius and the stars themselves are getting destroyed, the binary is being destroyed farther away because it's wider with the same gravity. So when a binary is destroyed, one of the objects is ejected and the other one stays with the same periapse but with a smaller semi-major axis. So this line here is the graveyard of the binaries. So the binary has two components, and unlike humans, which are like to be buried one next to each other when they die, here they separate at their death. One is being thrown away from the galaxy, and the other one is being put on that black line. After the survivor, the one that remains tied to the supermassive black hole, can still scatter on other stars. It may still go up and down in here. So if it came, for example, to this point, it will continue its up and down random motion and will die as a tidal disruption event. But if the binary was tight enough, that it is being torn only when it's closer to the black hole. So when it's torn here, it goes to this point. From this point, it may go up and down, but it will not die as a tidal disruption event. It will first hit that limit and turn by gravitational waves and become an emery. So I think that if the fraction of binaries in the galactic center is high enough, like what we know in here, especially for more massive stars, when it's almost 100%, then this breakup of binaries produces a strong enough source of stars close to the black hole, a fair fraction of the radius of influence, so maybe 2 orders of magnitude farther in than the radius of influence. And those stars there may either go up and down, scatter, and die as a tidal disruption events, or become emeries. And that increases the rate of emeries to about 10% rather than 1% that I discussed before. On this figure, you have all the observed S stars at the galactic center, so you can see where they are. So some of them have extremely eccentric orbits, some of them are more circular, and they're located here, and it's plausible that they came from the breaking of a binary. So at the moment that they formed as such a tied object to the supermassive black hole, they must have been on that black line. And then two-body scattering moved them up and down and brought them to here. The phase space in this region is much bigger, so this is why we expect to find them there rather than on the line. But there is a smaller phase space here, but still possible, and eventually they would become emeries, at least that side of the population. Let me skip that. I mentioned that already. So I would like to more or less summarize here. Using these analytical considerations that I discussed and taking into account the fact that binaries break up in the galactic center, we can estimate what is the smallest distance of a star from the supermassive black hole. So what is the semi-major axis in units of the Schwarzschild radius of a star from the supermassive black hole? And you can come up with an equation like that. This is the radius of influence divided by the Schwarzschild radius, which I told you is also 4 times 10 to the 6. M over M is 4 times 10 to the 6 inverse. And eta B is the fraction of binaries, because I claim that this inner part of this diagram is populated mostly by the breaking of binaries. So I need to know how many binaries are there. And I get that the semi-major axis compared to the Schwarzschild radius is about 10. So roughly the tidal radius may be slightly larger. So it's plausible that there is a star now close enough to the supermassive black hole that it transfers mass to the black hole if the fraction of binary is high enough. If the fraction of binary is low, then there are fewer stars injected in this process, and therefore the innermost star is slightly farther away from the supermassive black hole, but not by much. It's not a strong dependence on the fraction of binaries. So I think there might be something interesting for LISA and for emission from the supermassive black hole to be detected. I'll put my summary slide here. I think I went through most of these things, even though very roughly and quickly. And if you have any questions, I will be happy to answer. Thank you.
Thanks a lot, Graham. This was a very nice talk. Are there already questions? So I just remind everybody, you can ask a question by going to the list of participants, and then you can raise your hands there. Just maybe I start with a question. Is there observationally hope that we can detect some of stars so close to the black hole that are in this emeries region?
Right. So there are several problems. First, there is the dust that is making the galactic center opaque. But if you go far enough at the infrared, I think that problem you can overcome. Then there is a problem of resolution and of overcrowding, because that region is so dense. If your point spread function is not concentrated in a superb way. There is even a small leakage of 1% or 10% of the light of each star to the seeing disk on a 1 arc second, then you get a very high background, and this is why they cannot see small stars. So in principle, if you'd have the perfect telescope with diffraction limited resolution, you would be able to see smaller stars. And there is a chance that they exist because they are the majority of the stars. There are many more stars of half a solar mass than stars of 5 solar masses. So my guess is that there are orbits of stars below the ones of SO2, and then some of them may be doing some of the things I discussed in here. The other thing against that I haven't discussed is maybe there is a population of more massive objects, maybe massive black holes, not supermassive black holes, but remnants of stars that sank into the galactic center. Maybe they form a dominant population there and scatter the main sequence stars. I haven't treated any of that here, so I don't know if that's a valid thing, but this is another thing that I'm looking at. If that is the case, then there won't be any star so close. And when Lisa comes in, if there is any star that is sufficiently close to the supermassive black hole, we'll know about it.
Thank you. There are a number of questions. Maybe we go first with Andrea.
Yeah, thanks for a really nice talk. I'm curious about the stable mass transfer from a star onto the supermassive black hole. How restrictive is the regime in which this can happen in terms of distance from the black hole? And, do you need to have a close to circular orbit to avoid disruption of the star?
Yes, you need, okay. So, sure. These tidal disruption events are happening on extremely eccentric orbits. Just to, if we go here, I said that most of the sources of tidal disruption events is stars that started on a circular orbit at the radius of influence, but then became super eccentric. So they kept the original semi-major axis of 10 to the 6 Schwarzschild radius, but their periapse is 10 Schwarzschild radius, so their eccentricity is 0.999959 still. So these are tidal disruption events where the star gets destroyed. But if the star comes close slowly on a circular orbit that slowly shrinks, then it does, what is that? Then it does this motion in here. And there is nothing very special about it. You just start on a circular orbit, you emit gravitational waves. The orbit evolves initially by shrinking because the star itself also shrinks. And then when the star becomes small enough, the Kelvin-Helmholtz becomes too long compared to the gravitational wave timescale. It's basically because the star became too close to the supermassive black hole, so the gravitational wave emission became much stronger. So the main thing that shrunk is this one. And then the emission of mass from the outskirts of the star is on a time scale that is shorter compared to the time scale that the star can redistribute its energy. Therefore, it changes adiabatically, and adiabatic changes to stars are such that as the mass is going down, the star is inflating rather than becoming smaller. This is actually what keeps the stars stable. So as it brings mass onto the supermassive black hole, it will grow and therefore move away from the black hole to keep the orbit stable, to not more than overfill the Roche lobe. So I don't think there is anything particular in there. You just have to come on a circular orbit close to the black hole. And if you came on one of those, where is that? If you came on one of these orbits like that, this is still a very eccentric orbit, but as you move along this line, now you're on a circular orbit, still too far from the black hole, so you don't transfer any mass. Then you move on circular orbit, which go and shrinks, you still don't move any mass. Then you hit the tidal radius, now you start spilling mass to the black hole, but you're on a very circular orbit already because you've evolved through all that evolution in here. Now the orbit is already circular and you still keep it circular through the emission of gravitational waves. So I think if there are enough stars there, it will happen.
Okay, yeah, I guess I was asking because I was wondering if you expect those types of orbits so close to the black hole, but.
Yeah, so this is the calculation I tried to show at the very end, which depended on how many binaries are there, because the binaries are the sources of stars that are being thrown close enough to the black hole that can then evolve to become memories. And I found that the innermost star, statistically speaking, to the supermassive black hole should be roughly around the tidal radius, times some factor in here, which depends on the fraction of binaries, so maybe a few times that. So with some luck, we'll have a star right now there transferring mass into the supermassive black hole.
Thanks.
Okay, there are more questions. So Elisa, do you have, you can go. Yeah.
Oh, okay. Yes, thank you. So actually, exactly. Oh, first of all, thanks a lot for the very great talk. It's very interesting to me. And I was actually wondering about these binaries, because if I recollect correctly, the time over which you may destroy a binary stellar system near a supermassive black hole, more than the time scale. Let's say the fraction of surviving binaries may be relatively slow, because in order to survive, binaries should be relatively tight, should be hard, because the sigma, the velocity dispersion around the black hole is pretty large. So I'm a bit curious if you thought about the possibility that actually binaries just can't really survive in large number because of two-body relaxation effect that soften the binaries before they actually reach the point at which they dissolve because of the supermassive black hole.
Right. No. So this has to be encapsulated. You're right. This has to be encapsulated into this parameter. So if they are destroyed, and therefore the fraction of binaries in the galactic center is smaller than what we're used to, we'll have to plug it in here. But the binaries that are important for the process that I'm talking about are tight binaries, because as the binary object goes along this line, it gets tidally destroyed at a position which depends on how tight it is. So stars which are wide, you're right that they won't survive for other reasons. But they also, when they get dissolved, they do that far away from the black hole. So the black hole is down here. They do that far away from the black hole. They do that here, and they're not interesting for me. Tight binaries, they go intact, much closer to the black hole, maybe down to here. And then one is ejected as a hypervelocity star, and the other one goes all the way to here. So these are pretty tight binaries with which are almost hard, even with this high velocity dispersion that we have at the galactic center. It's still somewhat of an issue, and therefore I have this parameter here for what is the fraction of binaries in the galactic center, and that's why it's not really 10. It's somewhat larger, but I'm not sure exactly how much. So it's a good point.
Thank you very much.
So we have Judith. You have a question?
Yes. Hi, Ram. Thank you for the nice talk. I have a relatively basic question. So you were talking about supermassive black holes in the center of the galaxies, but what about intermediate black holes in globular clusters? And there were also detected hypervelocity stars from globular clusters, and we have some cases where they measured a few thousand solar mass, intermediate mass black hole in globular clusters. How much are these below the LISA detection limits when we will be able to do similar analysis in those cases?
All right, so I think if we keep the observation aside, the physics is the same. So I could say this is a supermassive black hole in the center of some globular cluster. Will have the same physics more or less, except that in some of the answers in here, for example, I use the M sigma relation for galaxies in order to know how is the radius of influence scaling with the mass of the supermassive black hole and so on. That's why I got answers which are super compact. They only depend on the mass of the supermassive black hole. So Yeah, in principle, that can happen for intermediate mass black holes as well. I think I'm not sure if Lisa is good exactly for those. Let's see, we can look at this in this. Oops. No, I have to go backwards. In that Lisa diagram that I showed before. What is that? Yeah. So this is the sensitivity of Lisa. So intermediate mass black holes, they will have higher frequencies because they're smaller. So actually, they're even better. Yeah. So you can see such things from there. That's a good point. Maybe it's a more appropriate thing. Maybe it's more frequent than the single supermassive black hole or the couple of supermassive black holes that we can observe in the center of our galaxy and in the center of Andromeda.
Yes, thank you very much.
Thanks.
Next question from Roma.
Hi, Aaron. Thanks for the talk. I have a question. So if I understand correctly, the order of magnitude that you gave, you expect the accretion rate of stars onto the black hole to be around 10 to minus 5 solar mass per year, right?
Yes.
And actually, it's small, but it's not crazy small, right? I mean, if you look at cosmological simulation using accretion rate mechanisms that are based on mostly gas accretion, that's what you get for relatively quiescent galaxies like ours. But so it looks like accretion of stars is competitive compared to accretion of gas in a sense, which is interesting because we don't do that at all in cosmological simulation. But I have a question regarding larger scale.
This is a standard number that is quoted for the rate of hypervelocity stars and also for the rate of tidal disruption events.
Exactly.
Actually, the observations suggest that tidal disruption events are even more frequent than that.
Okay.
And the outcome of a tidal disruption events, if half of when a tidal disruption event happens, where do I have that figure of a tidal disruption event? The original Martin-Rees diagram here. This is a star coming to be tidally torn. It reaches the tidal radius, and because the energy of that star is originally zero, or almost zero, because it comes from a semi-major axis, a huge semi-major axis, the radius of influence, you can think of it as a parabolic orbit with zero energy. And then exchanges between different parts of the star make half of it bound and half of it unbound. So if you know the rate of tidal disruption event, each star, half of it, eventually accretes onto the supermassive black hole. So if the event of tidal disruption events is 1 per 10 to the 5 or 10 to the 4 years observations claim, if we identify TDs correctly, I'm not sure about that, then half a solar mass from each star like that is accreted every time this happens. So the rate of 10 to the minus 4 or 10 to the minus 5 solar masses per year is, I would say, almost observationally inevitable.
Yeah, okay. But but for this, you need to reach the radius of influence. So now if you go back to like a simulation point of view,
yes.
What you can, if you have the resolution for, to resolve the radius of influence, then you can just compute the rate of, tidal disruption event and then deduce the accretion rate. But if you don't, which is the case for most, large scale simulations, you need to rely on a larger scale mechanism that will bring stars into the radius of influence. And can you give us a few examples of what mechanism can bring stars towards the ROI and feed the black hole that way on larger scale? That's what you discussed.
Well, let's see. I think I'm not sure a mechanism like that is actually needed. Let me try to think about it, because the radius of influence, by definition, is the radius where the mass of the stars is equal to the mass of the supermassive black hole. Mm-hmm. So if there is no mechanism that brings new stars, all you have to do is that the radius of influence will grow. Mm-hmm. Your definition of what is the radius of influence will go. Suppose the stars are not moving. So if the stars in the middle, they disappeared because they got accreted onto the supermassive black hole, then the radius of influence will grow, because by definition, you'll have to go farther away in order to have more stars. If scatterings far away are good enough to redistribute the stars and bring them again to the original radius of influence, then it will stay more or less where it is. So just by definition of the radius of influence is always full with stars, just by its definition.
But then the relaxation time will vary.
Will grow, yes.
Will grow.
Correct.
Okay.
Right.
Then you have a way to compute somehow the accretion rate, like that.
Yes.
Okay, got it. Okay, thanks.
So the accretion rate, it's a very simple result that is very easy to remember. It's one star per orbital time at the radius of influence.
Yeah, exactly. And these can vary. So okay, got it. Thanks.
And I guess a last question from Lucio.
Yeah, so thanks a lot. Very nice talk. And I was curious to see where exactly the Pirch signal will be in the LISA sensitivity curve. Is it really high enough in amplitude that I guess
yes.
It would be in the bottom right part? But...
Oh, I had it there. Let me see, where was that, Lisa, I think. So this is the expected signal if it's around the supermassive black hole in the Milky Way. And this is the expected signal if it's in Andromeda. And this is the LISA sensitivity.
Okay.
Okay, so when it's far away, it's under the sensitivity, but when it goes in, it's inside the sensitivity. I'm not sure how updated this figure. It might be a little bit old. The design of LISA keeps changing and the sensitivity curves are moving. So
yeah.
you see it penetrates deep enough that it's not it's measurable.
Yeah, no, okay, now I see that. I was confused because I'm used to see, because you said this is basically, I mean, it's a kind of emery, right? This type of signal, but it comes from the main sequence. Because the
exactly.
the emeries typically populate the bottom right part of the, or we'll say near the, the bottom of the valley in the sensitivity curve. So why is it here so different that you have such a different?
I think because I stopped when I could have continued this line, but I stop it where the star is filling its Roche lobe and transferring mass into the supermassive black hole, but a compact object won't do that. So I have to make sure that I'm saying it right, but yeah, I think that brings the endpoint of those stars here.
And the amplitude is larger compared to a typical emery. Why is the amplitude?
No, I don't think it's larger. Should be like a typical emery.
It's close.
This is just the black hole in the Milky Way. Yeah.
Okay. Yeah, maybe it's because
it's not an emery in some faraway galaxy.
Yeah. No, that's clear. Okay. Yeah, well, I guess we can chat later.
Okay.
It's very interesting. Yeah.
Is there, maybe Andrea, is there a short question that you still have?
Yeah, I wasn't sure if you were going to end. But yeah, I was wondering if the supermassive black hole has a secret intermediate mass black hole companion, if this would drastically change the rate predictions or your diagram in general.
It would, because such an intermediate mass black hole is very good at scattering objects. So it might take over the two-body relaxation at the area where that intermediate mass black hole exists. So if there is 1,000 solar mass black hole around, it may be more efficient in scattering objects than many more than 1,000 individual solar mass black holes or stars. And therefore it will change this diagram, and I haven't included anything like that in my discussion. So if we find that this diagram is not as populated as we expected it to be here, it might be because there is an intermediate mass black hole scattering these objects away. That is a fair possibility, especially if galaxies go through mergers and their black holes sync. So that could really happen.
Cool.
Thanks a lot for this seminar, for this talk. Also in the name of everybody.